So far, we have 3 facts that let us determine where the electrons are in atoms. Number 1, electrons in atoms can only have certain energies. We said those were energy levels and no energies in between. Rule 2 that we have here. Electrons in atoms don't have exact locations, but we can describe the probability of finding the electron in a certain region. Those are what we call the orbitals. And so we could say there's like a 90% chance of finding it in a certain region. And we said those orbitals have different shapes that we talk about as being like SP, D, F, G, and so on and like that. The next thing is that electrons fill the orbitals that are in these orbital shapes in order from the lowest energy subshells to the highest energy subshells. And remember, subshells are like your 1s, your 2s, your 2p, like that, an energy level with an orbital shape that goes together here. But they always fill from the lowest energy subshells to the highest energy subshells in order so that the atom has the lowest total energy. And that's that Aufbau principle, that building up principle in German. And so these are the 3 facts we know so far, but there's one other thing we're missing, and that deals with something called electron spin. So once scientists had worked out everything we talked about so far, and this is the quantum model of the atom, they could almost fully explain the emission spectra of elements. And so, what we sort of found is that because of the fact that these atoms have these different subshells, is that the lines in the spectrum don't just correspond to differences in energy levels, they also correspond to differences in subshells. And so if you had an electron that went from the 2p down to the 2s, that would create a spectral line, not just a drop from the second energy level to the first energy level. And so this is the reason why when we looked at some of those spectra that we saw, is that some of them had just lots and lots and lots and lots of lines. The reason why is because there were lots of transitions between different subshells, not just transitions between energy levels. They exist for the same reason, because there are discrete energy subshells just like there are discrete energy levels, and there's no energy in between the 2s and the 2p. Right, oh, sorry, that shouldn't be there, between the 2p and the 2s. And so electrons can only be at a 2p subshell energy or only at a 2s subshell energy and nothing in between. But there's still one other little problem here. If you look very closely at some emission lines, so you look at them first, it's like, hey, it's one line, but then you zoom in with your little magnifying glass and you look at them really closely and you see it's actually 2 lines that are very, very close to one another. And so that threw scientists off a little bit. So scientists came up with an explanation. They said we could explain this if electrons had an additional property called spin. It's called spin because originally they thought the electrons actually were spinning. It wasn't until later on they discovered the electrons actually weren't spinning. They sort of looked like they did. And so the property that they have that made them look like they're spinning, they just called spin because they'd been calling it spin before. And so it's not that they're actually spinning, it's just that they have a property that looks like they spin. So if these electrons have this property called spin. There are 2 possible spins that they can have. They're called spin up or spin down. Numerically, they're +1/2 and -1/2. Those are the numerical values for them, but usually we just call them in chemistry spin up and spin down for the 2 possibilities. Now, the argument is that if these electrons have 2 different spins, these little doublet of lines, these 2 lines that look like they're just one, the reason why they're there is because one of the lines is caused by the spin up electron and the other one by the spin down electron. And so that would explain why we get 2 lines sometimes that are really, really close together. They're really close together because those 2 electrons are both in the same subshell. In fact, they're actually in the same orbital, but one is spin up and one is spin down. And so that little difference there results in 2 slightly different lines that you get. Now, once they discovered electron spin, model of the atom and the electrons in it is almost complete. So another guy, Wolfgang Pauli, realized that if electrons had spin, that if you had 2 electrons in the same orbital, they have to have opposite spins. So if I have, let's say the 1s, because remember the 1s subshell has only 1 orbital in it because it's that spherical one right there. And so that would have 2 electrons in it. And according to Pauli, is that one of those electrons in here is going to be a spin up electron, and the other one is going to be a spin down electron. And so that has to be true if we have these electrons in different spins. And this is called the Pauli exclusion principle. Basically it says this: it's impossible for 2 electrons to be in the exact same quantum state in the atom. When we say quantum state, we basically mean in the same energy level, subshell, orbital, and spin, all combined. So another way of saying this is that an electron cannot be in the same orbital as another electron and have the same spin. You can have two electrons in the same orbital if they have two different spins. One is spin up and one is spin down, but you can't have two electrons in the same orbital with the same spin. Okay? Now, can you have two electrons that have the same spin? Well, of course you can, because there are only two types of spin, and so spin up and spin down. But you can have two electrons that have the same spin, like they both spin up, as long as they are in different orbitals. And so this is the Pauli exclusion principle. In a sense, all it's really saying is that you can't have two identical particles occupying the same space. This is actually the reason why if you put your hand on the table, your hand doesn't just pass through the table. Because if it went into the table, then you'd have some of the electrons in your hands occupying the same space with the same spin, the same quantum state as the electrons in the desk. They can't occupy the same space. This Pauli exclusion principle, the fact they're excluded from occupying the same space, is why that matter doesn't just pass through other matter. It's why when you sit down in a chair, you don't just fall through the chair. Is that these electrons in your pants and the electrons in the chair seat can't occupy the same space and have the same quantum states. And so as a result, they have to stay apart from each other, and it doesn't pass through. It just doesn't let them through. And so for the atom, this is important because it requires that the two electrons that are in each orbital have different spins. So two electrons can only occupy the same orbital if they have a different spin. Do they have to occupy the same orbital? So, if we have some orbital here, and so we're saying, hey, if I have a spin up and a spin down, do they have to go there? Well, we already know this. Atoms want to occupy, based on the Aufbau principle, subshells going from lowest energy to highest energy. And so if we had like a 2p subshell, p subshells have three orbitals. So I'll draw out three boxes to indicate those three orbitals. There are really sort of two possibilities of things that could happen here. Let's say I'm going to add two electrons. It could be that I have a spin up and a spin down. They both go in the same spot. Or it could be that one goes into this one and one goes into the next one, and they don't go right there. How do we know? Well, here's the logic. Electrons have a negative charge. And so if I were to put two electrons into the same orbital, like this, even though they have different spins, they're going to repel from each other. They want to get away. And so because of the fact they repel from each other, they're going to increase the energy of the atom whenever they're packed close together. Because they don't want to be there. They want to get away from each other. On the other hand, spreading them out, moving one into one orbital and one into a different orbital, notice they're both still at the same energy because they're both in the same 2p subshell. So we haven't changed subshells here, so we're not in violation of the Aufbau principle. It's not like we're jumping up to a new higher energy subshell without filling the previous one, because all three orbitals here are in the same energy subshell. They can spread out, and when they spread out, they repel each other less, and so they have a lower energy. So this is called Hund's rule. And so in Hund's rule, it says that electrons will occupy all orbitals in a subshell before they start pairing up in the same orbital. So let's say that I have a D, so let's say a 4D 4D subshell. Ds have 5 orbitals, and so we draw out 5 boxes for this. So let's say that there were 3 electrons in this 4D subshell. Well, according to Hund's rule, is the first electron would go into the first box. The second electron can go anywhere it wants to, except it won't go in the first box, because if it went in the first box, they'd be close to each other and repel. It would raise the energy of this atom. The third electron can go anywhere it wants to, as long as it's not in the same box as the first 2, right? Not in the same orbital as the first 2. And so notice that I didn't have to make them opposite spins. Why are they not opposite spins? Because they're not in the same orbital. They can be any spin they want to, as long as they're not paired up. If they're paired up, then they have to have opposite spins. So this would be if we had 3 electrons. Well, what if we had 5 electrons in this 4D subshell? Well, we already got 3. Number 4 would have to go here, number 5 would go here, and they're spread out because that we can't double up, we can't pair up any electrons until all of the orbitals in the subshell are occupied. Well, now they are all occupied. So what if instead of 5 electrons, we had 6 electrons? Where's number 6 going to go? Well, there are no empty orbitals at this point. And so that means the next electron is going to have to pair up. And so since it has to pair up, since the first electron was spin up, the second electron has to be spin down. If we had, let's say, 9 electrons in here, then we've already got 1, 2, 3, 4, 5, 6. So we have 7, 8, and 9 like this. And then we just have one last orbital at the end that has 1 electron left. And we said the d orbital could hold a total of 10, or the 4D subshell could hold a total of 10 electrons. And so that means the 10th one would go right here. And now the 4D is filled. If we had another electron, it would have to go from the 4D on to the next one, which, let's see, would actually be the 5P. So it would have to go into the 5P subshell next. So we can sort of see a little bit of this right here. So let's suppose that I just had 1 electron. Well, where would it go? It goes into the lowest energy subshell. So I'll do a little half arrow down there so it fits. And so it goes into the 1s. So that would be like hydrogen. What about helium? Helium has 2 electrons. And so where's that electron going to go? Well, it wants to go into the lowest energy subshell. It can't go to the 2s unless the 1s is filled. 1s isn't filled yet, so it's going to go in the 1s. And that's what we saw before. Remember, helium has that electron configuration of 1s2 because there are 2 electrons in the 1s, but one is spin up, one is spin down because of the fact they have to go into the same orbital. Now let's talk about lithium. Lithium has 3 electrons. So the first 2 go in the 1s, the next one goes in the 2s, like that. Okay? Let's jump ahead a little bit. Let's say we want to do carbon. All right? So let's look at carbon. Carbon, if you look at the periodic table, has an atomic number of 6. And so if it's a neutral atom, it'll have 6 electrons. So 2 in the 1s, 2 in the 2s. They have to be opposite spins because they're in the same orbital. That gives us 2 more electrons. They're next going to go into the 2p. And so the first one goes in the first orbital. Where's the second one go? Anywhere but that first orbital we see there. It has to go into the second one here. And so that they are in opposite, they're in different orbitals because of Hund's rule. Is they don't want to pair up until all of the orbitals in the 2p subshell are occupied. So what if instead of carbon, what if we had oxygen? Oxygen then has 8 electrons. And so we have 1, 2 down here, 3, 4, 5, 6. We need 2 more. 7 goes here. Well, what about number 8? Number 8 has to pair up. And since it has to pair up, it has to be a spin down to get around the other one here. Now note that in these cases, I've always started off with spin ups. The reason why is because you really don't know when the electrons go in, whether they're spin up or spin down, and it really doesn't matter which one goes in first. It's entirely arbitrary whenever you put in 1 electron in an orbital about whether or not it's spin up or spin down. It's your choice. You can do it either way. The only thing is you have to remember is if they pair up, one has to be spin up and the other has to be spin down. The general convention is the first one you put in is spin up, but it's not like physically that's actually what's happening. All right, so whenever we're talking about this, we have a set of final rules for our electronic structure. And so here are those rules. Electrons and atoms can only have certain energies. Those are the energy levels and no energies in between. Second rule that we have here, electrons and atoms don't have exact locations, but we can describe the probability of finding an electron in a certain region, which are the orbitals, those S, P, D, F, and S has 1 orbital, the P has 3 orbitals and such like that. So it's just a specific region. Those were those weird shapes that we've seen before. Next rule, electrons fill orbitals in order from the lowest energy subshells to the highest energy subshells, that Aufbauer building up principle. The idea is the atom will always have the lowest total energy, so it'll fill up the 1s subshell first, and only when that's filled do electrons start going to the 2s, and only when that's filled do they go to the 2p, and they always fill from low energy to high energy. So rule 4 is electrons can only occupy the same orbital, 2 electrons can only occupy the same orbital if they have different spins. You can't have 2 spin up electrons in the same orbital, you can't have 2 spin down electrons in the same orbital, but you can have 1 spin up and 1 spin down, and that's that Pauli exclusion principle. And then our last rule we have is electrons will occupy all orbitals in the subshell before they start pairing up, and that's Hund's rule. So we can use these rules now to do another way of showing where the electrons are in atoms, and these are called orbital box diagrams. And so these will show not just what subshells are filled, but also which orbitals are filled. So in an orbital box diagram, boxes are drawn for each orbital in a subshell, and the electrons are indicated by arrows, sort of like we did before, with an up arrow indicating a spin up electron and a down arrow indicating a spin down electron. So it's sort of similar to what we did back here, but instead of having to draw it out in like 2-dimensionally where it's showing the energy like this, we draw it out flat, sort of like you're seeing right here. So first thing you do is you draw out what your subshells are. So 1s, 2s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Those, of course, are low energy to high energy in that Aufbau order here. The 1s, because it's an S subshell, will have only 1 orbital, so we draw 1 box. The 2s, since it's an S subshell, will have 1 orbital, so it's 1 box. The 2p, since it's a p subshell, will have 3 orbitals, so we draw 3 boxes. Then s, 1 box, p, 3 orbitals, 4s would have 1 orbital, 3d would have 5 orbitals, and so on and so forth. And so this is the way we draw out the boxes. Once you've done that, and really you only need to draw boxes for suborbitals that have some electrons in them. You don't have to draw out the whole thing for every one, just enough to show which ones have electrons in them or which subshells have electrons in them. That you sort of do it like this. So let's say that what we're going to do is we're going to draw out the orbital box diagram for lithium. So lithium has 3 total electrons, so the first 2 would go in the 1s. So we'd have first one goes here. The second electron has to also go in the 1s, so it has to be spin down because we can't go to the 2s subshell unless the 1s is filled. That gets 2 of our electrons. The third electron then would go in the 2s, and so we draw it out like this. And so this right here, showing an up arrow and a down arrow in the 1s box, and just an up arrow in the 2s orbital box, would be the orbital box diagram for lithium. If we did that, we wouldn't need anything else out here. We wouldn't even write those down at all. We would just do this. Note that you have to draw the box, put the arrows, and label which subshells are there as well. Okay, so that's how you draw out an electron box diagram for lithium. What if, instead of lithium, we went to something a little more interesting? What if we said that let's look at sulfur? Okay, so with sulfur, we look at the periodic table, and it tells us that sulfur has a total of 16 electrons. So for sulfur, we'd have 1, 2, put those arrows on there, 1, 2, 3, 4. Now the next ones are going to 2p, so 5 would go here. What about 6? Can't double up because it's in the same subshell. Remember that according to Hund's rule, they have to be in different orbitals until that all the orbitals in that subshell have at least 1 electron. They're all occupied, then it doubles up. So we have 1, 2, 3, so actually that's 4, so actually that's 5, 6, 7, and then 8, 9, 10 right here. Now the 2p is filled up, so let's go to 3s. 11 and now 12 have to go here. Then it's going to go 13, 14, 15, because of Hund's rule says they're not going to double up in the same orbital until each subshell or each orbital has at least 1. We need 1 more electron to get to sulfur, so 16, where's it got to go? Now it's got to double up because there's no more room in the 3p.